Okay, let's dive into some raw numbers today. Just those lists of data points, ungrouped data. What are they really telling us?
Exactly. And our goal here, looking at the material you sent over, is to pull out the key ideas about two really fundamental ways to understand these lists. The mean and the median.
Right, finding that sort of center point.
That's it. Two different ways to think about what's typical in your data.
So we're digging into the sources, how to calculate them, sure, but maybe more importantly, what these numbers actually mean. Pun intended, I guess.
Well, yes. And why you might lean towards one or the other, depending on what you're looking at.
Okay, let's unpack the first one then, the mean. Most people probably know this as the average.
It is. Technically, the sources define it as the sum of all your observations divided by the number of observations. You often see written as sigma x over n.
Sigma just meaning add them all up, right?
Precisely. Sigma is just shorthand for summation. Add everything up, divide by how many everythings you have. It's like finding the fair share.
Got it. So the source example, heights of 6 boys, 146 centimeters, 154, 153, 160, 157, and another 160.
Right.
You add those up, comes to 930 centimeters. Then divide by the 6 boys.
And you get 155 centimeters. That's your mean height. Pretty straightforward calculation.
Yeah, simple arithmetic.
But here's a neat property the sources highlight. The sum of the differences of each number from that mean, it always adds up to 0.
Oh, interesting. How does that work?
Well, think of the mean as the balance point. The source uses numbers like 2, 4, 6, 8, 10. The mean there is 6.
Okay.
The deviations are 2 minus 6 is minus 4, 4 minus 6 is minus 2, 6 minus 6 is 0, 8 minus 6 is 2, and 10 minus 6 is 4. Add those up. Minus 4 minus 2, 0 to 4.
They cancel out 0, like a perfectly balanced seesaw.
Exactly. The mean is that unique balance point.
Okay, now this part I found really useful, how the mean changes if you, adjust all the numbers.
Ah, yes. The properties. If you add a constant, let's say a, to every single number in your list, the mean just increases by a. Same if you subtract.
And multiplication, division.
Same idea. Multiply every number by a, the mean gets multiplied by a. Divide by a, the mean gets divided by a. It's a direct linear relationship.
So in that source example where the mean was 13.5, if they added 3 to every single data point.
The new mean is just 13.5 plus 3, which is 16.5. No need to recalculate the whole sum.
Wow, okay. And if they multiplied everything by 4?
Then the new mean is 13.5 times 4, 54. It's a handy shortcut.
Definitely saves some calculation time.
And the sources show practical uses too, like finding a missing number if you know the mean, or say correcting the mean if you realize one number was copied down wrong. It directly impacts the sum and therefore the mean.
Okay, so that's the mean. Sum-based, balance point, affected by every number. But then there's the median. Tells a different story, right?
It really does. The median is all about position. It's the middle value after, and this is key, after you've arranged the numbers in order. Ascending or descending doesn't matter, but they have to be ordered.
Ordering first. Got it. So how do you pinpoint that middle value? It depends on how many numbers you have, doesn't it?
It does. Depends on n, the number of observations. If n is odd, simple.
Simple how?
The median is just the value of the single middle term. The formula is the n plus 1, 2, the term.
Yeah.
So if you have 11 numbers, like in one source example,
I've got 11 numbers.
then 11 plus 1, 2 is 6. The median is the value of the sixth term in your ordered list. The source said that value was 31.
Right. But what if n is even? No single middle number then?
Correct. If n is even, you look at the two middle terms, specifically the n2th term and the very next one, the n2 plus 1th term.
The two right in the center.
Yes. And the median is the average of those two values. The source example had 10 numbers.
So n10 even.
Right. So you look at the 1 or 2 fifth term and the 1 or 2 plus 1 equals sixth term. The source says those were 47 and 49 in their ordered list.
And the median is halfway between them.
Exactly. Average of 47 to 49, 47 plus 49, 2 is 48. So 48 is the median.
Okay, makes sense. And the source mentioned changing just one value could shift the median. They swapped a 62 kilogram weight for a 35 kilogram one.
Yes, and because that changed the order and potentially which values were in those middle spots, the median changed. I think it went from 49 kilograms down to 47 kilograms in that case.
So it can change, but maybe not as wildly as the mean might if you introduce a really extreme number?
That's often the case, because the mean uses every value's magnitude. One very large or very small number, an outlier can pull the mean quite a bit.
Whereas the median just cares about what's in the middle positions once ordered.
Precisely. It's less sensitive to those extreme values. It's focused on the positional center, not the value center, if you will.
So we've got the mean sum divided by count, the balance point. And the middle value of ordered data.
2 ways to find the center.
Both useful, but they can give you quite different pictures of the same data, especially if the data is skewed.
Which leads to a really important consideration. When you encounter data out in the world, say, average income or average house price, which average do you think is more representative of the typical situation?
The mean, which could be skewed high by a few mansions or billionaires.
Or the median, which tells you the point where half the people earn less and half earn more, regardless of how much those top earners make.
Definitely something to chew on next time you see average reported anywhere. Thanks for digging into this with us.